Hello. So I'm Katie Leachman, and this is a presentation on geometric transformations in music that's based on some research I did about 8 months ago. I'm really looking forward to sharing this with you because it's something that I am very passionate about. I love the connections that are possible between math and music, as well as other disciplines, to see how math truly does relate to and describe just about anything. So, without further ado, here is how to apply geometric transformations to 17th century Baroque music. So to start off, here's a bit of background on Johann Sebastian Bach. He was a famous composer known for writing all kinds of music, piano music, choral music, and organ music to name a few. But he actually didn't become very well known until he was dead. It's surprising because he wrote a lot of music and discovered the harmonies that are used in almost all music today. We even call him the father of harmony. In the piano world, he's most known for writing the Well-Tempered Clavier, which is a collection of preludes and fugues. I'm not going to go into much detail about that, but from here I'll show you how transformations work in fugues. So, here, our first one is displaying the subject and the answer of a 4-voice fugue. Here's the audio if you'd like to know what it sounds like. I've come up with my own graphic representation of fugues. As you can see, I've taken the notes from the score and recorded them on a graph where every other horizontal line on the graph is a line on a musical staff. Each note is placed on the graph by its pitch and value. I've labeled the subject in red and the answer in orange. Next, I connected the notes to make triangles. And you can see here that they look about the same. But I'm going to show you that between the subject and answer is actually a very precise transformation. So here I used Sketchpad to find the translation vector between the sets of triangles, and it turns out once I found it and told Sketchpad to translate the subject's triangles by this vector, they fit perfectly into the answer's triangles, which is a pretty cool way to see a basic transformation that exists in music. Here is the proof of the translation if you'd like to pause and read over it, but for now I'll move on to another example. Here is what the next fugue sounds like. This graph shows a reflection about a line between the two voices, which you can see here in red and green. I threw in the translation for this one just for fun, but the reflection is the main focus here. So you've heard the clip that it's real music, and famous music at that, but you can see that it's still represented mathematically. Again, here's the proof if you'd like. Now, the final example is actually my favorite. It's the fugue in D minor, and here I'll go ahead and give you the audio. You can see how the 3 triangles plus the point are going to be shifted in some way, but not quite how yet. So here, and it is a bit jumbled, so I apologize for that, you can see that each set of triangles includes a glide reflect from the subject to the answer. Once again, I have the proof, but for this example, I've made an important note. You may have noticed that in this example, the entire answer was not transformed by the same glide reflection. There is a distinctive musical reason for this. An answer in a fugue can be either real or tonal. If it were real, the glide reflection would be the same for the entire answer. In other words, would essentially be exactly the same, just moved over a bit. But this one is tonal. Simply put, it was necessary for Bach to slightly adjust the answer to make it sound better and resolve, which resulted in a slightly different transformation. The isometry, however, still applies. To conclude, fugues are an awesome way to begin showing isometries in music. It's a pretty cool thing to study 2 completely separate things like math and music and yet have them overlap in such powerful ways. I really enjoy doing research that allows me to combine these 2 things that I'm passionate about. So I hope that those of us who are interested in math can take away from this an empowerment to do research in any field we care about and then combine it with math. Finally, musicianship is just as much a mathematical and analytical process as it is a creative one. So, thanks for watching.